So as we have seen over the past few days, pH is a really big deal. Just how acidic or basic a system is. And if you want to maintain that pH and keep that pH constant, buffers. That's the way to go. So whether it's the buffer or the common ion effect, they're really kind of the same thing. We can keep the pH of a system constant. It's through the common ion effect that we reduce a lot of the hardness in our water in San Antonio's aquifer. Buffer systems are really important in agriculture. In our own bodies, we have a buffer system. We need to keep our pH in a certain range, otherwise we're going to have trouble. Coca-Cola, it contains phosphoric acid, and if you consume a lot of Coca-Cola, well, the acidity in your body would increase, so something has to react with it. And what happens is that the calcium gets leached from our teeth and bones to buffer that. And, well, that's not good. So the argument is what's better, Coca-Cola or beer? Well, I'll leave that for you to decide. The common ion effect. This below reaction may be used to describe the common ion effect, the ionization reaction of the acid HCN, in water. How do we write it's an acid, how do you write ionization reactions, or the Ka reaction? Remember, it was the conjugate acid goes to the hydrogen ion plus the conjugate base. If the reaction is at equilibrium, and each of the following occurs, would the total moles of hydrogen ion increase, decrease, or remain the same? Okay. We're adding HCN. So if we're adding HCN, now we have too much reactant. Equilibrium should shift towards product, so that would be more hydrogen ion. Let's try this again. We're adding sodium cyanide, and it's solid. Remember our solubility rules. Anything with these alkali metals is 100% soluble, so we hardly ever look at them. So we are really adding cyanide. So if you're adding cyanide, now we have too much product. Equilibrium will shift towards reactants. We'll have less. (10 mils of 0.085 molar nitric acid is added. Well, we're adding, recognize nitric acid, strong acid. We're really adding, you really don't look at the nitrate, we're adding hydrogen ion, so we'll have more. Strong acid. 5 mils of calcium hydroxide is added. Do you recognize this? Strong base. So we're adding hydroxide. Well, that will remove the hydrogen ion, right? So we're going to lower, we'll have less hydrogen ion because it will be reacting. Buffers. A buffer is a solution that has the ability to resist slight changes in pH, just as we mentioned earlier, when small amounts of an acid or a base is added. All buffers are mixtures of a conjugate acid and a conjugate base. Sound familiar? Conjugate acid, conjugate base. Therefore, any solution containing a weak acid is a buffer. We are going to use the Henderson-Hasselbalch equation to determine the pH of weak acid or buffer solutions. So this is our equation. The pH of the buffer will be pKa plus the log of the concentration of the conjugate base divided by the concentration of the conjugate acid. Well, what is pKa? It's kind of the p function. If we have pH, we know that's negative log of H. So if we have pKa, that's just the negative log of whatever your Ka is. Okay? Now, it'll be a lot easier to use this equation to calculate the pH of a buffer if we rewrite the Henderson-Hasselbalch equation this way. And the reason why we can do that is because the conjugate base and the conjugate acid, these compounds that are in the same container, they have the same volume. So the volume cancels, you're just left with moles. So that can lead us to trick questions like this. We're going to be adding things to our buffer and trying to predict what the pH is going to be. What if we just add water? It's an aqueous buffer. We just add water. Well, look at your equation. The only way to change the pH of a buffer is to change pKa. Well, you can't do that because you have to change the entire weak acid. Well, we're not doing that. We're just adding solvent. You have to add more conjugate base or add more conjugate acid or change that amount. We're not doing that. We're just adding water, so there'll be no change. With different buffer problems and a game plan for each type of buffer problem. Here's our first type of buffer problem. Calculate the pH of the resulting buffer solution when 20 mils of 0.8 molar hydrogen fluoride and 50 mils of 1.2 molar lithium fluoride are mixed. Now, what makes this a buffer? Remember, it's the weak acid. If you have a weak acid, it's definitely a buffer. Hydrogen fluoride, buffer. So we're going to use our Henderson-Hasselbalch equation, find pH, and we'll have our answer. Let's start by looking up the pKa, right? Well, we can't find the pKa, but we can find the Ka. And the Ka of hydrofluoric acid is 6.8 times 10 to the negative 4. So pKa would be the negative log of 6.8 times 10 to the negative 4. What's that? 6.8 times 10 to the negative 4 log negative 3.17. Okay, so my pH is going to equal 3.17 plus the log. We have to find the moles of conjugate base, find the moles of the conjugate acid, and divide the two, and we'll have our answer. Here's our conjugate acid. How do you get moles? Well, we know the volume, 0.02 liters, right? Move the decimal place over 3 places. Big N is just moles per liter, so 0.8 moles per liter. My liters cancel, I'm in moles. So 0.02 times 0.8, about 0.016 moles of my conjugate acid. 0.016 moles. The conjugate base. Conjugate base, same idea. I'll have 0.05 liters times 1.2 moles per liter. 0.05 times 1.2 0.06 moles of fluoride. Remember, lithium we don't care about. That's an alkali metal. When you have an alkali metal with anything, it's always 100% soluble. That was our solubility rules. So that's the purpose of the lithium. The lithium is an alkali metal, no acidic or basic properties, so we kind of just imagine it's not there. Let's see, 0.06 moles fluoride on top. Okay, so what's my answer? 0.06 divided by 0.016 equals, take the log, plus 3.17. I get about 3.74. The pH of my buffer solution. Okay, problem type 2. It wouldn't be much of a buffer if we didn't add some acid or base to it. So that's what this question's about. Calculate the pH of the buffer that we just prepared when 10 mils of 0.2 molar HCl is added to the entire buffer solution. So use the exact same equation. our modified Henderson-Hasselbalch equation. Our pKa we said was 3.17. Now we just have to figure out the moles of conjugate base and the moles of conjugate acid. The moles of conjugate base is F minus. The moles of conjugate acid is HF. Okay. When you add an acid, what is going to react? A base will, right? So you add an acid, well, we can just write it's a strong acid. When you add an acid, the base reacts, the conjugate base, and what do you make? HF. So here's our strong acid. So what does a buffer do? A buffer actually converts a strong acid to a weak acid. So the pH is still going to get a little acidic, but not near as acidic as it would have by adding a strong acid and nothing reacted with it. So when we add a strong acid, the conjugate base is going to react, right? And it's going to form HF. So our moles of F minus have to go down. Before we had 0.06. We had 0.06 moles of that stuff. But it has to go down. How much does it go down by? It's right here. The moles of the strong acid that you added. And what's that? Well, that's 0.01 liters times 0.2 moles per liter. Liters cancel. 0.01 times 0.2, well, 0.002 moles. So that's the amount that it has to go down by. Okay, the moles of HF, that forms. So if 0.002 moles of HF reacted, 0.002 moles of HF have to form. So before we had 0.016 moles of hydrogen fluoride. Now we're going to have 0.016 plus 0.002. Okay? So we'll have pH would equal 3.17 plus the log of 0.06 minus 0.002 divided by 0.016 plus 0.002. We get our answer. 0.06 minus 0.002 equals 0.058 divided by, I'll use some parentheses here, 0.016 plus 0.002, close parentheses, hit equals, take the log, add 3.17, about 3.68. Okay, now these calculations are somewhat involved, so I like to look at it. We added an acid, and the pH went down, as it should, right? Because it's 3.68. It was 3.74. So this is looking correct. It went down just a little bit. Didn't go down a lot. It went down a little bit. The buffer's doing its job. Okay, calculate the pH of the buffer solution, the same buffer solution we had that we made in number 1, but now we're adding a base. It's being added to the entire buffer solution. If we're adding a base, again, don't look at the alkali metals. We're adding hydroxide. Now it's going to react. The conjugate acid. So our conjugate acid in our buffer is going to find those hydroxides, react with them. What will it form? HOH is water plus what's left over, fluoride. So what did the buffer do? The buffer took a strong base and converted it to a weak base. So the solution will get a little more basic, but not near as much as it would have if something didn't react with that strong base. So, same story. My pH is going to equal pKa, which we said is 3.17, plus the log. Now my moles of conjugate base, moles of conjugate acid, what were they originally? Before they were 0.06, and 0.016. Those are the original numbers. 0.06 and 0.016. Okay, now I'm adding a base. So the moles of HF is going to react, right? So it'll decrease. The fluoride, that's forming. So it'll increase. So I'm going to add for my conjugate base, subtract for my conjugate acid. Those numbers have to change in that order. By how much? Let's figure it out. It'll be the moles of the strong base. 0.012 liters times 0.15 moles per liter. 0.012 times 0.15, about 1.8 times 10 to the negative 3. 1.8 times 10 to the negative 3. Okay, so let's try it again. 0.06 plus 1.8 times 10 to the negative 3, it equals, divide it by, use some parentheses, 0.016 minus 1.8 times 10 to the negative 3, close parentheses, it equals log plus 3.17, 3.81. Okay, so our pH should have gone up a little bit because we added a base. It was 3.74. Add some NaOH, it goes to 3.81. That's looking good. Okay, the last type of buffer problem is when they don't add it to the entire buffer. You got to be careful. Okay, they didn't add it to the entire buffer. So let's try this. Calculate the pH of the entire buffer solution when 12 mils of 0.15 molar NaOH, the same amount, but it's added to only 1/2 of the buffer. Okay, so our pKa is still 3.17. Our moles of conjugate base, so we're adding a base, you get a base. That kind of helps me. Add a base, get a base. So find out the moles you had there originally, and I'm going to add. What did we say it was? 1.8 times 10 to the negative 3. Add a base, get a base. So the acid has to be reacting. I'm going to be subtracting the 1.8 times 10 to the negative 3 on the bottom. But what's that original amount? Okay, it was 0.06 and 0.016, but we only added it to half the buffer. So you don't have this entire 0.06 moles of conjugate base and entire 0.016 moles of conjugate acid. You only have half. So multiply it by your fraction of half. And then see if you can get your answer. So if we clean it up, it's going to look like 3.17 plus the log of 1/2 times 0.06 minus, or sorry, it's plus 1.8 times 10 to the negative 3. 1/2 times 0.016 minus 1.8 times 10 to the negative 3. Okay, 0.5 times 0.06 plus 1.8 times 10 to the negative 3 equals, divide by, parentheses, 0.5 times 0.016 minus 1.8 times 10 to the negative 3, close parentheses, equals log 0.71 plus 3.17. You get about 3.88. Okay, does that answer make sense? Adding a base, the pH should go up. It was originally 3.74. It went up to 3.88. Sounds good. If we added this volume of NaOH to the entire buffer, it went to 3.81. But if you add it to only half the buffer, it goes up a little bit higher. Good. It should, because there's not as much buffer. So those numbers are looking correct. Okay, here's a few buffer problems. See if you can get them. Use the modified Henderson-Hasselbalch equation to see if you can predict the pH of these buffer solutions. So my modified Henderson-Hasselbalch is pH equals pKa plus the log moles of conjugate base all over moles of conjugate acid. Okay, my conjugate base is right here. That would be 0.05 liters times 0.25 moles per liter. 0.05 times 0.25, about 0.0125 moles. So that's my conjugate base. My conjugate acid is right here, 40 mils of 0.2 molar HCN. So that would be 0.04 liters times 0.2 moles per liter. 0.04 times 0.2, 0.008 moles. Okay, so my answer here is going to look like this. pH equals pKa, which is the negative log of 4.9 times 10 to the negative 10, plus the log of 0.0125 all over 0.008. So 0.0125 divided by 0.008 equals log minus 4.9 times 10 to the 10 negative log, about 9.50. So if you have to write some intermediate steps there, go ahead. Now, what is the pH if 100 mils of 0.01 molar HCl is added to the entire buffer system? Okay, add an acid, get an acid. So my pH is going to be, well, the negative log of 4.9 times 10 to the negative 10. That part doesn't change. Plus the log of 0.0125. Let's put in the original moles. Okay. Add an acid, get an acid. So if I'm adding an acid, I'm going to get an acid. That means the conjugate base is reacting. So add an acid, get an acid. The plus is going to be in the denominator because that's where the moles of conjugate acid is. So what are we adding here? We are adding, what is that number? 0.1 liters times 0.01 moles per liter is going to be 0.001 moles. 0.001. So 0.025 minus 0.001 equals, divided by 0.009 equals log minus 4.9 to 10 to the negative 9.42. So my pH did go down a little bit. It was at 9.5, now it's at 9.42. Looks like a good number. A buffer is prepared by adding 300 mils of 0.82 molar HClO and 250 mils of 0.75 molar sodium hypochlorite. They give us the Ka. What's the pH of the buffer solution? pH, okay, 3.5 times 10 to the negative 8. The negative log of that is 7.45. So I'm going to figure it out right away. Plus the log, moles of conjugate base divided by moles of conjugate acid. So that would be 0.25 liters times 0.75 moles per liter divided by 0.3 liters times 0.82 moles per liter. So that's going to be 7.45 plus the log 0.25 times 0.75, 0.1875. 0.3 times 0.82, 0.246. Okay. I got around 7.33. That's the final answer there. What would be the pH of 100 mils of the buffer, to which 25 mils of 0.35 molar HCl has been added? So they're doing two things here. We're not adding this acid to the entire buffer. We're only adding it to 100 milliliters of the buffer. Okay? So remember the game plan? pH is going to equal my pKa. We said that's 7.45. 7.45 plus the log moles of conjugate base on top, moles of conjugate acid on the bottom. We're adding an acid. If you add an acid, get an acid. Plus, minus, right? Add an acid, get an acid. The moles of conjugate acid will increase. The moles of conjugate base will decrease. Well, by how much? Let's figure that out. That's going to be 0.025 liters times 0.35 moles per liter. I'm going to get about what? 0.025 times 0.35, 8.75 times 10 to the negative 3. Okay. Now, how many moles of conjugate base and conjugate acid did I have there originally? Here are the numbers. 0.1875 and 0.246. 0.1875 and 0.246. Okay, now that's the entire buffer though, so I can't multiply it by the entire, right? Can't use the entire buffer. What's the fraction? I'm using 100 mils. What fraction is that? 100 mils divided by the total. What's the total volume of my buffer that I made? Well, it had 300 mils and 250 mils. That's 550 mils. So my total is 550. So what's 100 divided by 550? 0.18. So that's my fraction. It's an oddball fraction, but it works. 0.18. Okay. See if we can get this to work. 0.18 times 0.1875 minus 8.75 to the 10 to the negative 3, it equals, divided by, parentheses, 0.18 times 0.246 plus 8.75 to the 10 to the negative 3, close parentheses, it equals, log plus 7.45, 7.12. Does that make sense? Yeah, it went down a little bit more than it did before because it was 7.33. Okay. So the idea here is to use our modified Henderson-Hasselbalch equation to get the pH of weak acid solutions. And what we're going to do is we're going to be adding acids and bases. So just remember, when you add an acid, you get an acid. So you'll be adding the moles of acid that you added. And the base is what reacted with it, so subtract. That number will be going down.